M2003 Corona and Masks. It's a mini competition problem from the HKOI Online Judge website. In the GitHub link below, you can find the problem in its entirety. So go ahead and read the problem and come back and solve the problem together. So first, let's play around with the problem a little bit first to gain some intuition and insight into the pattern of the underlying problem. And here's the input sample I'd like to go over with you. In this case, N is 8, so there are 8 pharmacies, and here is the graphical depiction of the problem. You see there are locations, and there are also inventory count, which is the number of masks here. Alright, let's take a trip to the first pharmacy toward the left. It took 1 second, and now the number of masks there is 7 instead of 8. Okay, and now you keep walking toward the left. So time goes by. As you can see, the inventory is depleting in every single pharmacy here. You keep walking, and when you get to the second pharmacy toward the left, only 7 masks are left, and which makes it a total of 14 masks from this trip so far. And then you keep walking toward the left, and notice how the third pharmacy ran out. It's out of stock. And as you keep walking toward the left, it stays at 0. And when you get there, you're still at 14 masks from this trip. And then you go to the fourth pharmacy on the left. Now the inventory went down from 50 to 30 over there, and that makes it a total of 44 masks from this trip. Okay, so let's give those numbers some names. A prime and cum A prime. Those numbers are pretty easy to compute, and I'll leave it to you to write the code to calculate these numbers, and they will be very useful later on as we solve the problem. Okay, now let's see how we can implement a simple and correct solution. So this is the graphical depiction of the problem again. That's what we started with. And let's take a trip to the first pharmacy toward the left. And then we pick up 7 masks. 1 second has elapsed. Now let's turn right back, go home. Now 2 seconds has elapsed. But then remember, some masks are gone on the right hand side. Because time goes by, masks are sold. So now how many masks can he still collect from the right side, starting from home at time equals to 2? Well, it's 73, right? Plus the 7 that he had from the trip to the left, it's a total of 80. So that's the mass from this scenario. Now let's consider another scenario. He takes a trip to the second pharmacy to the left, and he picks up 14 along the way, and then he turns right back home. 8 seconds has elapsed, and some masks are gone on the right hand side. Only 57 is left. And then he had 14 from the left hand side, remember? And that's a total of 71. Not as good as the first scenario, right? Okay, let's try take a trip to the third pharmacy on the left and then return home, and that took 20 seconds for the round trip. Because the third pharmacy is sold out, he's still at 14 from the trip to the left. But a lot of masks are gone on the right hand side in that 20 seconds. And so 42 is left to be collected on the right hand side, and that's a total of 56 masks from this scenario. So he's doing even worse, because he's doing no better on the left hand side, but it got a lot worse on the right hand side. Let's see if he has any better luck from the fourth pharmacy. So he takes a trip to the fourth pharmacy on the left and go home, a round trip of 40 seconds. He can pick up 44 masks. So because there are still a lot of masks in the fourth pharmacy. And now at t equals to 40, a lot of masks are gone on the right hand side, and only 22 can be collected. And that's a total of 66 from this trip. A little bit better than the previous scenario, but not as good as the first scenario, which turns out to be the best scenario, 80 so far. And then you repeat the same thing in the opposite direction, and the best scenario will win, and that's your answer. Okay, so here's the pseudocode to implement that simple approach. for every pharmacy on the left side, you take a trip there and buy up all the masks on the way. That's masks L. Well, the time it took to do that and a round trip home is 2 times the distance to that pharmacy. And then you calculate how many masks are still remaining on the right-hand side at time t, and then you go there and collect all the masks that's remaining, as much as possible. The sum of masks L and masks R is what you're trying to maximize. And of course, you have to repeat the same thing in the opposite direction, taking a trip to the right-hand side first, and then go back to the left side and collect all the masks. Well, 2 parts needs a little bit expanding. They are non-trivial. Take a trip to the left side and buy up the masks. And then how do you calculate and adjust the masks that are depleting on the right side as you took that round trip to the left? Well, the first part is straightforward. Remember, we calculated QA prime, or at least you did, right? So that's just a matter of looking up that number. And then the second part can be implemented that way. You go through all the pharmacies on the right-hand side, and then you reduce the inventory by time t, the penalty, and you also reduce it by the distance of that pharmacy from home. You clip the lower bound at 0, and there is your pseudocode. This will score you full points on subtasks 1 and 3. Okay, you ready for the full solution? Remember, the simple and elegant solution is order of n squared in time complexity. It's because of the nested for loop here. So how do we optimize it? Well, let's look at the underlying problem pattern a little bit more. So here is the data, and it turns out if you sort A prime, you can calculate mask R a lot more efficiently. Why is that? You see, until t equals to 3, the mask R that you can collect on the right side is decreasing at a rate of 4 per second, because 4 pharmacies, all of them are still in stock. But after t equals to 3, 1 pharmacy has run out, and now the rate of decrease is 3 per second. 3 pharmacies are still in stock. And after t equals to 5, only 2 pharmacies are in stock, so it's decreasing at a rate of 2 per second. And after t equals 11, only 1 pharmacy in stock, and the rate of decrease is now 1. So if you plot the chart of masks R as time goes by, here's what it looks like. It started with a slope of -4 until t equals to 3, and then the slope would become -3, and after t equals to 5, the slope would becomes -2, and after t equals to 11, the slope would now be -1. So can you see that? You can see the pattern here, right? You don't have to calculate masks R from scratch every time. You can build on the previous mask R and just reduce it by the current prevailing slope times the number of seconds elapsed since the last time you dealt with the masks R update. So how would you implement that? Well, here's one way to implement it. The general idea is called incremental reduction. It's kind of the converse of partial sum. In partial sum, you're doing incremental summation, but here you're doing incremental reduction. You keep track of the masks R, and you keep reducing it at the slope that's currently prevailing. And so what you need to keep track of, other than mask R, is the in stock, which is the number of pharmacies that's still in stock. You also need to keep track of the last t, which is the last time you updated the mask R. And that's it. Take a look at the pseudocode. It's a pretty simple way to do incremental reduction, and that's all you need to score 100 points in this problem.